Okay, today's lesson is on the quantum model of the atom, and that probably sounds like a super scary model, and it is very complicated, but most of this information is beyond the scope of the course. So if you find yourself getting confused, we will make sure to break it on down at the very end to where you guys will know what you're responsible for knowing moving forward. But there is where it is worth our time spending time talking about because it's a lot of cool information, and it is our modern, most current model of the atom that we have based on our understanding so far. Okay, so let's talk about the quantum model. So here is the progression of the atomic theory, or our understanding of what the atom looks like. Here we go, John Dalton's billiard ball model. Then we had J.J. Thomson with his cathode ray tube experiment discover the electrons. Then we had Rutherford with his gold foil experiment discover that positively charged nucleus there in the center of a bunch of empty space where the electrons are somehow located. Niels Bohr then said, okay, those electrons are now actually orbiting the nucleus like planets in specific energy levels, right? And now we are moving to this guy named Erwin Schrödinger, and it looks like his model was about 13 years after Niels Bohr's. And his model is called the quantum model of the atom. Now, I put the picture of this cat down here because some of you guys may have heard of the term Schrodinger's cat, and most of y'all probably were like, we had never have known what that has meant. When we get to that topic, we do not need to know what that is, but I did provide some fun video links if you guys wanted to kind of nerd out and learn about that topic a little bit more. Well, let's talk about Erwin Schrödinger's quantum model. So the story of the atom continues. So the Bohr model was correct, kind of, for the hydrogen atom. So keep in mind, the hydrogen atom only had one electron. Watching one electron move up and down throughout the energy levels is kind of easy for us to track and observe. But when I get into other elements besides hydrogen, I'm getting into more electrons and electrons that are found in higher energy levels. So as a result of this, the Bohr model failed to explain specific energies absorbed and emitted by atoms of these other elements. So the quantum mechanical model. Erwin Schrödinger was an Austrian theoretical physicist who proposed our current model for the atom, which is based on mathematical calculations. And y'all are like, oh no, do not be afraid. So with the quantum mechanical model, electrons are not described as these particles that orbit in these fixed orbits, but more like these wave-like entities with a likelihood of being in a specific three-dimensional region called an orbital somewhere outside of the nucleus. So Schrödinger came up with a really complicated equation. This is his equation down here. No, we are not doing anything with this equation. I always like to put it on my PowerPoint slides because there's a lot going on here for us to get to this quantum mechanical model of the atom. So his equation does not tell us the exact location of the electron, but rather it describes the probability that an electron will be at a certain location in the atom. So these blurry regions indicate where the electrons would exist in the highest probability. So the basis of this quantum mechanical model allows us to determine, one, the allowed energies an electron can have. What that means is where electrons are allowed to be in the energy levels. We know that the first energy level is closest to the nucleus, so it's the lowest energy. And as I go further and further away from the nucleus, those are higher energy levels. So the quantum mechanical model does allow us to figure out what energies are allowed for an electron. It also allows us to determine how likely it is to find an electron in a particular location within that energy level. So as a result, today we say that the electrons are in a region outside of the nucleus called the electron cloud. So here we've shifted our thinking of what the atom looks like from these orbits of electrons orbiting the nucleus to this just kind of general cloud where we only have an idea of the probability of where an electron may be. So presenting Schrödinger's model of the atom. the quantum model. So I'm going to go ahead and I think I'm going to zoom in quite a bit here. You have a space on your notes page for us to draw the quantum model of the atom. And first of all, there's a small nucleus in the middle. So we're going to point to that nucleus and label it the nucleus. And then you're going to see a bunch of dots now coming off of that nucleus. And this is probably the most difficult of my models to draw. Because what we're trying to do here is we're trying to create a gradient where most of the dots are closest to the nucleus. And as I move to the outside, the dots are further and further apart, right? So this requires a little bit of technical skill. I do not grade work based on quality of art. The main thing here is you can try to achieve a visible understanding of what we're dealing with here. Okay, but once again, these dots are the regions showing where electrons exist in the highest probability. This quantum model is all about the probability of things. Okay, so moving on. Okay, so this stuff is like super simple to measure, right? No. This is an actual quote from Niels Bohr. It says, if you aren't confused by quantum mechanics, you haven't really understood it, which I have not dove into that much of quantum mechanics, but I feel like every time I attempt to do so, it is very, very confusing to me. Okay, so here is our first topic that we're going to talk about that is probably beyond the scope of the course. So we're going to talk very, very, very briefly about this. This will not be something that you will be tested on. So I wanted to explain why it is hard for us to figure out where these electrons are. So it says the quantum world cannot be observed directly, but instead by using instruments to try to measure it. And so then there is a problem with the fact that simply the act of measuring it will disturb the energy and the position of the subatomic particles that we're trying to look at. So this is what's known as the measurement problem. So basically, in order for me to try to observe what an electron looks like or where it is, I have to indirectly fire a photon of light at it, hoping to get a reflection back for me to see. Now, in the process of doing that, I can actually disrupt where that electron is. And so when I'm collecting the information, it is inaccurate in some way. And the topic of Schrodinger's cat has to deal with this concept that there is apparently a cat in the box. And if the cat is in the box, you do not know if the cat is alive or dead. And if you open up the box, then the question has already been answered. So you cannot know what's inside. Anyway, there's a cool video on that. So the second thing says that furthermore, there's a limit to how precisely two pairs of physical properties of a subatomic particle can be known simultaneously, like the position of a particle and the momentum, meaning how fast it's traveling. I have trouble being able to look at both of those things at once because the more accurately one of them is known, the less accurately the other one can be known. Or if I more accurately know this one, the less accurately that one can be known. This is also due to the measurement problem because as you can see, me trying to look at where that electron is and where it is going, the act of trying to measure it disrupts its position, okay? So that's known as the Heisenberg uncertainty problem. Okay. Once again, beyond the scope of this course, but these are probably some terms that you have maybe heard before and are like, I've always wondered what that is. Well, it is now involved here in this quantum mechanical model of the atom. Okay, well, so we're already confused. Let's take it back to the simpler stuff. Remember when we had the cute little energy levels, right? And the electrons jump up and down and gave perfect little spectra lines of light. So we said that that energy can be quantized. That is still basically true. But we know that the picture is a little bit fuzzier than what we were looking at before. But let's scale it back and let's still think of, even though it's a new electron cloud, we're going to still think of it inside of that cloud having energy levels. So there is still quantization in the electron cloud. Electrons are found in these various energy levels around the nucleus. And remember, energy levels are like the rungs on a ladder. The lowest rung here of the ladder corresponds to the lowest energy level. And an electron can jump from one energy level to another, but it cannot exist and hang out in between energy levels. Okay? And in order for electrons to move, they must gain or lose just the right amount of energy to get from one energy level to another. And this specific amount of energy that's required is called a quantum of energy. And if the energy is released as light as it falls down, that is when we see a photon of light. So this is a review, and you're like, why are we talking about this again? Because we're now going to expand on this in terms of our quantum model. But as you can see, I did some arrows here in different colors. So my jump from energy level 1 to 2, I did red, because if you'll remember from our electromagnetic spectrum, red is the lowest energy color of our visible spectrum. So a short jump like that would give off probably a low energy form of light. And then my longest energy jump from 1 to 4, when he falls back down to 1 again, he would give off a much higher energy form of light because that jump required a lot more energy to get to. Okay, so now let's not think about it as rungs as a ladder. What if we thought about these energy levels as different floors of a hotel? Okay, and walking up the stairs to get to a certain floor would require some quantized amount of energy to get there. And once you get to a certain floor, there's lots of options of different rooms that you could go into. Like they have the single hotel room. They have a double hotel room. They have like the presidential suite hotel room. Let's keep going with this. So welcome to quantum numbers, the electron cloud hotel. So as complicated as all of this stuff can be, we can dumb it down to a better level of understanding if we think about these electrons just going in a hotel and occupying up rooms and sleeping in beds, okay? So with this, locating an electron in an atom is as simple as trying to find a person in the hotel. So let's take it one step at a time and figure out what these quantum numbers are and how they can help us determine the location of electrons in an atom. Our first quantum number, whose symbol is little n. The first quantum number is energy level. What energy level is an electron found in? Well, with my hotel analogy, the energy level would be a hotel floor. What floor of the hotel is my electron found in? Now, we've kind of talked about this before, right? Energy levels are assigned values in order of increasing energy. We would say that the first energy level is energy level 1, or n equals 1. Now, y'all are knowing where that n comes from because that stands for this first quantum number technical term. So 1, 2, 3, 4, etc., all the way up the hotel floor. Great. So, okay, we have figured out where our electron is, what floor he is. We have identified his first quantum number, or his first identity of his location. Next, once we get to the specific floor, we got to figure out what room is he in. Okay, so our second quantum number is what sub-level within an energy level, what type of sub-level that electron is found in. So these are different types of rooms. So within each energy level, the electrons are located within different sublevel. Each sublevel has a unique shape. So looking here, I did some floor plans of different size rooms. Yeah, we got a small single room. We got a little bit bigger double room. We got a giant master suite. The same can be said for these different sublevels inside of that hotel floor, okay? Here is one sublevel. He's very small. Not a lot going on in that room. Here is all this stuff in a different sublevel. Oh my gosh, that looks crazy. It is okay. That is just a hotel room, you guys. And here is another sublevel. Got lots of stuff going on in there, okay? And there are technically 4 different sublevels. There's an S, P, D, and F. So S, P, D, and F are the different types of rooms that you can find in a hotel. Okay. Which brings us to the third quantum number, what orbital you are in. So once I've identified what energy level I'm in, or what hotel floor, then I figured out what room the electron is, meaning what sublevel. Then I walk into the room, and depending on the type of room, there are going to be different numbers of beds in there. So the next step is to figure out, well, what bed is the electron sleeping in? So it says, within each sublevel, the electrons are located in different regions called orbitals. Each of the different sublevels have a different number of orbitals. But here's the trick, like my picture of a bed shows, that bed can only hold 2 people. That is a double bed. Well, same thing with electrons. Each orbital bed can hold 2 electrons also. Okay, so how many numbers of beds are in each one of these different rooms, the S, P, D, and F sublevel rooms? Let's see. The S sublevel, my S room, you guys, is not going on in that room. It only has 1 orbital. And that shape of that orbital is a sphere. Okay? So since I can have 2 electrons in 1 bed at a time, even though the S orbital or S sublevel only has 1 orbital or 1 bed, 2 electrons can actually fit inside of it. But just 1 bed in the S room. Moving on to the P room. It's got 3 beds. Whoa, now we're getting weirder shapes. So the P room beds or orbitals are this weird dumbbell shaped. I'm kind of wondering if the P means peanut shape, because to me they look like a peanut. I feel like at some point in time I have learned this in my life, but that part is not important where the P came from. But it's got 3. So once again, S had 1, P had 3. Now the D room has 5 orbital beds, which are weird clover leaf shaped. This one has got a different shape. You guys, we're not responsible for knowing the shapes of these, and I'm going to show a video here at the end that really tells us these shapes are probably not the full picture either, but the main thing is that our D room has 5 beds. That's a giant room. So you thought that one was giant. We're getting to our last type of room, the F room. That is like the master suite party room. There are 7 beds, 7 orbitals in an F room, you guys. Whoa. And they are, yep, we don't know what shapes those are. There's some pictures for you to ponder at, but that is a weird shape of these F sublevel orbitals. But there are 7 of them. Okay. And then we are to my last quantum number. I have figured out what hotel floor they are in. I have figured out what type of room they are in. I have opened the door to that room. I have found what bed they are sleeping in. No matter that this seems very stalkery, I'm getting to my 4th quantum number, and I'm going to see what direction they are sleeping in that bed, okay? So these electrons, they're going to get in the hotel, and if they double up with another electron in that bed, they're going to be strangers, and they are not going to sleep face to face. One electron is going to sleep down, and the other one is going to sleep up. We call that spinning in an electron. So within each orbital that is fully occupied with 2 electrons, one electron is going to spin up, the other one's going to spin down. So these electrons must spin in opposite directions. So what we got is we got what hotel floor you're in, what type of room you're in on that floor, which bed you're sleeping in that type of room, and what direction in that bed you are sleeping. So with this is how we try to figure out the probability of the locations of the electrons, okay? So I want to show this real cute video, it's a pretty nerdy video of what the electron cloud probably more likely looks like.
Atomic orbitals have long been a source of frustration for me. On the one hand, you have simple cartoon diagrams that make them feel friendly, but which are so varied and vague they don't really convey much beyond the basic idea that atoms have a nucleus and some electrons. Some people try to take the cartoony diagrams and make them feel more random or quantum, which is an improvement, but they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically accurate or technically inspired, but none of which feel like they give me a sense of what's actually going on. Like, what does this blobby thing have to do with orbiting electrons? Is the electron inside it, or on the surface? Why do some of them have blobs and others donuts? And why are some of the donuts rainbow-colored? I want to know what an atom looks like, and I want that picture to actually have something to do with the nitty-gritty reality of atoms, since they are indeed real things. You know, like how a diagram of the solar system is both a totally not-to-scale caricature, and yet also represents the very real idea that the planets all orbit the sun in roughly the same plane, and that some are farther out and some are closer in, and if it's animated, we get to see that the closer planets complete their orbits more often. It's a nice picture, and that's what I want for atoms, a good picture. There are a few things I'd like that picture to get across, some of them because they're important for the physics of atoms, and some of them because they're questions my brain wants answers to. Like, where is the electron? How fast is it going? How much energy does it have? How big is this picture relative to other pictures? Of course, the wave-particle nature of quantum mechanics means some of these ideas, like the electron's position, don't translate exactly from our everyday intuition to the atomic scale. But there is a way of thinking about wave-particle duality where you picture the wave function as a bunch of water, and the particle as a speck of dust in that water. The particle is mostly guided by where the water goes, and the water is guided by the equations that determine how water behaves depending on its circumstances. And if you apply the mathematics of that idea to atomic orbitals, and then render it in 3 dimensions, here's what you get. Isn't it beautiful? Here's another. And another. And another. In fact, I made a bunch of these, and they're all mesmerizing and beautiful, and isn't the ground state of the hydrogen atom just so cute? And aren't the excited states so majestic? There's so much structure and detail in them, I just love it. You can see patterns in the orbitals, and you can get a sense that they actually are orbitals. I mean, something is orbiting. Okay, so I do have to be clear. The dots don't each represent a separate electron. The whole collection represents the wave function of a single electron, and the individual dots represent all the places that electron could be. A higher density of dots means a higher probability of the electron being there. The bigger orbitals are the ones with higher energies, because electrons with more energy are more likely to be far away from the nucleus. The motion of the dots is showing the flow of the wave function, and does correspond to an extent with its actual angular momentum, though they're not electron trajectories. Unless you think Bohmian trajectories are real, in which case they really are electron trajectories. I'll let the philosophers of physics fight that one out. But the point is, these visuals are created by representing actual electron wave functions in a visual language that our brains can understand, that of objects and light and shadows and motion in 3D space. There's actually stuff orbiting, and they're pretty. I hope you like them as much as I do. Oh, one final thing. I 100% get that these are not easy to draw, so if you want a cartoon representation of an atom that's simple but more closely based in atomic physics, here's my proposal. It's based on the orbitals from the p block of the periodic table. One of them has the electron orbiting one way, one in the opposite way, and in the third one the electron is orbiting the same amount, but around some perpendicular direction, and we can't know which is why the dots aren't moving in the middle orbital, and why I've drawn a dotted line and question mark for the sideways circle. And if you want, you can add an electron to each orbital, or 2 electrons, one oriented spin up and one spin down. This is a Minute Physics approved cartoon representation of an atom. But really, the beautiful 3D ones are where my heart is.
Okay, so there you have it. Those are what we really think that is going on with those electrons inside of the electron cloud. But like I said, I would recap with what we are responsible for knowing in terms of this quantum mechanical model stuff. But you guys, we've done it. We have gone through the progression of the evolution of the atomic model theory. Dalton to Thomson to Rutherford to Bohr and now to Schrodinger. So we've got them to thank. All right, so now I'm going to drop down to my document camera. And I want us to work out something together. I said we'd be drawing something on the back of this notes page. So I'm going to have everybody flip their notes page over. And I'm actually going to zoom out a little bit more so that you guys can kind of see how far I'm wanting us to kind of write on this page, or how much space the stuff that I'm going to be drawing is going to take up. So we're going to draw this electron cloud hotel right here on this back of the page, okay? So we're going to give this a title. We're going to call it the Electron Cloud Hotel, okay? And I probably will zoom in just a little bit so we can see. And up here, we are going to write our 4 quantum numbers and what those quantum numbers represent, and what hotel analogy term that really means for us. So our first quantum number was the energy level. And the energy level for my hotel is the floor. Sorry, there was something underneath my paper that made my pencil stop. Okay. Now, in the atom, there is a first energy level. There is a second energy level, third, there are energy levels all the way up to 8. So our hotel's got 8 floors here, okay, you guys? Okay. Now our second quantum number, after I've identified the energy level, I zone in on what sub-level that electron is in. And the sub-level is the room on that floor. And once again, there's different types of rooms. We have an S, P, D, and F rooms. And then once I've identified the sub-level, my third quantum number tells us to find the orbital within that sub-level. So orbital. And the orbital is the bed. Yes. Okay. And here we're going to write how many beds each room has, or how many orbitals each sublevel has. So remember, my S room had 1 bed. I don't know why I put it into parentheses there. I should put a comma, right? And then I have my P room has 3 beds. And then my D room has 5 beds. And finally, my F room has 7 beds. Lots of beds going on in the F room. Okay, and then my fourth and final quantum number, so I'm like not quite halfway down my page. You do not have to do your spacing perfectly. I'm just giving some suggestions. But my fourth quantum number is figuring out the spin direction. Right? And my spin direction is basically my sleeping direction, right? So on my sleeping direction, we are stating that there are 2 electrons per bed, right? And they sleep in opposite directions. Okay? Okay. Now I'm going to zoom out a little bit more. The rest of this space, we are going to draw our hotel. Our hotel probably is only going to go up halfway because the hotel floors, as I get higher and higher, have a lot more going on. That's going to make us trail off the page here. We're going to work through some examples and right up here in a little bit, something else up here in a little bit. But for what I want you guys to do right now, I want us to draw an arrow going up the side over here, okay? And we're going to label this arrow increasing energy. Okay. Now, if you remember when we looked at the energy level diagrams of Bohr's model, we had lines representing energy levels, and y'all probably saw this arrow pointing up, letting you know as you go up the energy levels, you're increasing your energy. Same thing, as I'm going up the hotel floors, I'm increasing energy. Just like for the electrons, when you go from one energy level up to another, you have to take in energy to accomplish that. Well, I don't know about you, last time I climbed upstairs to get to the top of a hotel floor, like, that's going to take some energy input from me. Okay, so we're going to draw the first 4 floors of our electron cloud hotel. So we're going to draw floor number 1, 2, 3, and 4. Okay, so I'm going to zoom in a little bit. And what you will need for your hotel is you are grabbing 4 colors or colored pencils, okay? If you want to know what colors I am using the color blue. I am using the color orange. I'm using the color green and red. So if you want to pause the video and grab the same colors as me, or if you want to do different colors, just realize we'll be using these colors for coloring our periodic table according to what this hotel also shows. Okay. All right. So these 4 different colors are actually going to represent my 4 different sublevels, my rooms. My S colored pencil is going to be blue. My P colored pencil is going to be orange. My D colored pencil is going to be green. And my F colored pencil is going to be red. So let's go to the first energy level, my first hotel floor. Guess what, you guys? There is only 1 type of room on the first floor, and it is an S room. And remember, an S room has only 1 bed. So you guys, we are going to put a line in the blue color, and that line is going to represent that 1 bed, okay? And underneath that bed, that orbital, we are going to write 1S, because that lets us know that's the bed in the 1S room. That's all you got on the first floor, you guys. Now I got to move up to the second floor. On the second floor, there's an S room on the second floor. Once again, it's still an S room, so it's still only going to have that 1 bed. But now it's on the second floor, so we're going to call this room the 2 S room. But that's not all on my second floor. My second floor has another type A room. Get out your P colored pencil. Mine is orange. So there's a P room on the second floor. Keep in mind, a P room has 3 beds. So I'm going to draw 1, 2, 3 beds, and collectively underneath those beds, I'm going to write 2P. Awesome. Okay. That's all the rooms that there are on the second floor. I'm moving up to the third floor. Third floor also has an S room, 3S. Third floor also has a P room. We're going to call him 3P. The third floor has another room. The third floor has a D room, and a D room has 5 beds in it. So we're going to draw 1, 2, 3, 4, 5. And some of y'all are predicting what's going to happen on further energy levels, and you were like, ooh, I better squeeze in my spacing here, and I always somehow mess it up. Okay, so that all represents my 3D room. That is a very lightly colored green. I'm sorry about that. Okay, moving up to the fourth floor. I've got a 4S room, right? And I'm going to go underline my S right there. I have a 4P room, 1, 2, 3. I have a 4D room, 1, 2, 3, 4, 5. So that's 4D, hard to see, 4D. And then there is an F room on the fourth floor, so grab your F colored pencil. Mine was red. So I'm ready to go. I think I said this first one was, I hope I said that first one was orange. Oh my goodness, you guys. So I have red, 1, 2, 3, 4, 5, 6, 7. So that are the beds in an F room. This is on the fourth floor, so it is the 4F room. Okay, I only drew 4 levels of this hotel. I know we said that the hotel goes all the way up to 8, but that's because everything past the 4th floor has all of the 4 different sub-levels too. So there will be on the 5th floor 5S, 5P, 5D, and 5F, etc., etc., etc. Okay, so what does this mean to me? We're going to do an example, okay? We're going to say, okay, we're going to look at oxygen. So I'm going to zoom in again, and on my periodic table that I have not colored yet, I see oxygen. He's got an atomic number of 8, which means he has 8 protons, and he has 8 electrons if he is neutral. So let's pretend we're dealing with a neutral atom of oxygen. So we're going to write up here, example, we have oxygen, 8 electrons. Okay. Now, how are all these 8 electrons going to fill up all of these rooms and beds in this hotel? The key thing about the Electron Cloud Hotel and about the electrons is that they are tired and they are lazy. All of this process, moving up the stairs and walking down the hallways to the different rooms, is going to require some energy. And electrons like to exert the lowest level of energy possible. So what that means is they aren't going to crawl on up to the fourth floor and start picking up beds over here if there's stuff that is still available for them to sleep in on lower floors. So they fill energy levels from the lowest energy level first and have to then continue on. Okay, so here we go. My first out of the 8 electrons, he is walking into this hotel. He is ready to go. Here he comes. Oh, the first floor. We are excited about that. Great. I see the room, an S room. I see a bed in there. I'm going to lay down in that bed. And we remember that laying down direction is called a spin direction. So we're going to draw an arrow up. It's like a half of an arrow up. Sometimes you'll see a full arrow. Both notations are totally fine. So that's where the first electron goes. We still got 7 more to go to get to our 8. So the second electron comes into the hotel. He says, oh, I'm opening up the door to the S room. There's already an electron in that bed, but I really don't want to have to go to the second floor unless I have to. So I guess I'm gonna double up in this bed, but this other guy is a stranger, so I'm gonna make sure I spin in the opposite direction. So the second electron in an orbital will spin down. Okay, we're ready for the third oxygen electron. He comes in. Uh-oh, everything in the first floor is full. Gotta go up to the second floor. He starts walking down the hall. he's going to grab the first room. He is not going to walk all the way down to other rooms because he's tired. He's lazy. He wants to go to bed. Opens up the door to the S room. He's like, great, here's a spot for me to sleep. He spins up. The fourth electron comes in, has to go to the second floor. He opens up the S room and says, okay, there is still room for me to sleep. Okay, it's not ideal. I'm going to have to spin in the opposite direction, but I don't want to have to go to the P room unless this one was already full, and it is not. So he is going to occupy the second spot in that orbital spinning down. So we're halfway full here with our oxygen electrons. I've got 4 in there. I've still got 4 more to go. So the next electron comes in. He walks down. S room is full. He walks into the P room. He opens the doors. There are now 3 options of beds for him to pick, but he is tired. He is going to sleep in the bed that is closest to the door. He's not walking to the other side of the room. He is going to sleep in that first bed spinning up. Now, the 6th electron is the exciting one. 6th electron comes up. Yep, second floor. Yep, you're full. Open up the door to the P room. He's like, okay, there's still some room or there's a available spot for me here in this room. And there are lots of options. Keep in mind, these electrons are all strangers. They do not know each other. And last time I checked, if you open up a door of a room and there are lots of possible beds, you are not going to sleep in the same bed as a stranger unless you absolutely must. The same goes for electrons. So that electron is like, yep, not doing that, goes over to the next bed, and he will spin up in the next bed over. So my 7th electron, he's coming in hot. He's opened up the P room. He's like, oh, good, there's a bed still available for me. The last electron, the 8th electron, he hops on in here. He's like, okay, opens the door to the P room, and he's like, oh, well, I've got to double up now. But he's still lazy, so he's going to double up in the first bed. He does not want to walk away or walk all the way over to the other side of the room. So that's basically how these electrons come in and occupy this hotel. They start from the lowest energy level. They work their way up. They fill up the rooms. If a room has more than one bed, they fill it up one at a time before they double up and spin down. This is exactly the way the Electron Cloud Hotel works. And the cool thing is, you guys, is if I were to turn this upside down, and I'm going to show you in a second, our periodic table beautifully maps out this Electron Cloud Hotel as well. But I want us to bounce back to us talking about these oxygen atoms and recap what it is that we did down here, okay? And on these oxygen atoms, we would say the configuration or the representation of how oxygen's electrons fill up would be like this. I would start at the bottom, and you're going to tell me what room was filled up first. Well, the 1s room. Great. 1s. And then the next room, and then you're going to tell me how many electrons in that 1s room. 2. So I would put a superscript 2. 1s2. So that's the first room that was filled. The next room that was filled, I have a 2s room. So I'm going to go 2s. How many electrons are in that 2s room? 2. The next room we filled up was the 2p room. 2p. And how many total electrons are in the 2p room? 4. This is what's called electron configuration. Writing this out, showing the order of all of these different rooms and beds being filled up and how many electrons you have in all of those rooms, okay? So I want y'all to look at here is the biggity big numbers represent my energy level, right? So these are the energy level. And once again, those are the floor. And then the letters of the alphabet, my S, P, or D and F, we'll get there too. Those represent the sublevel, which is the room. And then this, the numbers up at the tippity top, that represents the number of electrons in the sub-level, okay? Which once again, the sub-level is the entire room. Okay, so what I want y'all to do now is to turn to your periodic table. Have your Electron Cloud Hotel nearby. And what we're actually going to do now is we are going to, I already done this, so I want y'all to just look and see. I told y'all the Electron Cloud Hotel was like an upside down periodic table where we have what we call here the S block. The S block I have colored blue, and that is the same color that I colored my S rooms on my Electron Cloud Hotel. So go ahead and grab the colored pencil that you use for your S rooms, and you're gonna color the first two columns or the first two groups of the periodic table that same S level color. Do not forget helium over here. He's being awkward. We are going to consider him as part of the S room. It would be nice if he fit perfectly there like Tetris, but apparently that is not the case for us. And you can pause the video if you are coloring. I'm going to keep moving on. You are going to grab your P colored pencil. P for me was orange. And you are going to color this block of the periodic table orange. This is your P block of the periodic table. So I'm going to let y'all pause. And then joining in, my D colored pencil was green. And so I colored, my transition metals here. We're going to talk about the transition metals next unit, but I'm going to color them, that D color. This is my D block. And then finally, my big old room, my F room, I used the color red for my F room. So I'm going to color my F block the color red. And then also down here at the bottom, I made a little key where each sampling of my colors represent each block, as we would say. So you can pause the video and then come back. We're going to label some things. So my first row or my first period of the S block, guess what? That's the 1S room. And then I hop on down to the next row, and that's the 2S room. And then I keep moving. I got this wide gap to cross. And then the next room I fill up is the 2P room. Then I go down in the next row, and then I fill up the 3S room. Y'all see where we're going here? And then I fill up the 3P room, and then I fill up the 4S room. Here's something a little bit weird. My D block starts with the number 3. You were like, why is that not 4D? Well, the Electron Cloud Hotel is a little bit freaky in that for some reason, the electrons that come in after they finish filling up 3P, it is too much energy for them to walk all the way down the hall to get to the 3D room. They would rather hop up one hotel floor and grab that room right there next to the stair exit. Okay, that does not matter. Y'all are like, now the hotel is all confused. It does not matter because your periodic table tells you as you scan from left to right, top to bottom, the order of filling up these rooms, okay? So once again, I will notice that my S rooms, they started on the first floor. I had an S room on every single floor. So I will label my S rooms, this first one, 1S, 2S, 3S, 4S, 5S, 6S, 7S. Yeah? And that's also the 1S. Now my P rooms from my hotel drawing, I saw a P room happen on on the second energy level and every other energy level higher than that. So my P block starts with 2P, 3P, 4P, 5P, 6P, 7P. And then my D rooms, we started seeing those on the third floor. So my first D row is 3D, 4D, 5D, 6D. And then finally, my F rooms, we started seeing those on the fourth floor, 4F, 5F. And some of y'all are like, she told me that there were 8 possible energy levels within the atom. And yes, there are, but we have not created elements that are big enough to occupy anything on that 8th energy level. But there is a possibility of 8 energy levels. So what we're doing here is you guys are going to start looking at your periodic table, and I will be able to ask y'all things like, great, give me the electron configuration for aluminum. And you're just going to start with your finger, moving your finger from left to right all the way down until you get to aluminum, saying what sublevels you are filling up and how many places it takes for you to get into it. One thing I do want you to notice, we know an S room has 1 bed, and we know 2 electrons can fit in that 1 bed. Guess what? My S block is 2 elements wide. We said my P rooms have 3 beds. Well, I can fit 2 electrons in it, so I could potentially fit 6 electrons in a P room. That's why your P block is 6 elements wide. And my D block with 5 rooms, 2 electrons are My D block with 5 beds with 2 electrons per bed, that's 10 total electrons that can fit in a D room. High, 10. Wide. And then my F with 7 beds, 14 total electrons. That is why this F block totally is 14 elements wide, right? Okay, so the key thing here is that if I were to say, okay, what is the electron configuration for aluminum? You would go 1s, well, I've moved through 2 elements. 2s, I've moved through 2. 2p all the way through that, so 2p6. 3s all the way through, so 2. And then I'm going into the p room, 3p, and I'm stopping at aluminum. So I'm only 1 element into that 3p room, so it would be 3p1. So 1s2, 2s2, 2p6, 3s2, 3p1. And this electron configuration is what we are going to be focusing on next time. So welcome to the Electron Cloud Hotel, you guys. This is the extent of what you will need to know in terms of the quantum numbers, right? Basically, energy level is a floor. A sublevel is a room, an orbital is a bed, and the spin direction is just what direction you're spinning in that bed. We're going to expand on this, but turning each one of these scary sciencey words into the hotel analogy term makes this picture much clearer to see. So that was super fun, and I'm excited to do electron configuration with you guys next time.